Hello everyone, welcome back to Linked Frequency. In this tutorial, we are going to learn about how to design a lithium-ion battery charging circuit using a TP5100 IC. This is the 19th tutorial of practice project for PCB designers, and I am Vaibhav Sugandhi, passionate PCB designer and technology startup founder. In this video, I'm going to show you how to design a small PCB like this to charge our lithium polymer or lithium ion batteries, which are most widely used in IoT devices and most of the electronic embedded systems nowadays. Because every device that we are designing nowadays, our requirement is being portable. So if we want to make any product portable, then we have to use a battery inside. And whenever we use a battery inside, we should always include a charging circuit along with that battery. That's why this TP5100 IC, which is manufactured by Chinese, and this IC is very great suitable charging circuit for most of our applications. Why? Because it is capable of charging a single cell as well as two cells. That means if we want to use a 4.2 volt lithium ion battery pack, then also we can use this module to charge it. Also, if we want to go for a two cell in series, which is all about 8.4 volt, then still this module is suitable for us. Let's jump into the datasheet of TP5100 IC and try to understand how exactly the design standards works. First thing is, I'll go to the datasheet, and if I scroll it to the top page, then you can get to know that this is manufactured by Nanjing Expansion of Electronics Microelectronics Company Limited, based out of China. This complete data sheet is actually or originally is from Chinese. That's why when it is converted into English, you can see that the characters are overlapping or having some error in the character display and all that thing. Duplication of characters or duplication of words as well. Just ignore that. Whatever we want from this data sheet can be learned by using this simple data sheet. First thing is a 2 ampere switch buck converter inside this particular module, which means it is capable of doing a fast charging with a 2 ampere of a current rating for 8.4 volt battery pack as well as for 4.2 volt battery pack. 4.2 volt doesn't mean that 4.2 volt at a nominal voltage, it is a maximum voltage. 8.4 is a maximum voltage, which means a 3.7 volt lithium ion battery can be charged, as well as two series of 3.7 volt lithium ion battery can be charged with this particular chip. And if you scroll it a little bit down, you can see absolute maximum ratings here, and also a certain characteristic which are essential to read before designing anything with respect to this IC. The minimum charging current with a slow charging is 0.1 ampere, and the maximum fast charging current is 2 ampere. And this can be programmable. Programmable in the sense you can set the charging current based on the external resistor, which helps you to set the speed at which you want to charge your battery based on application, based on the requirement. This is how the typical circuit looks like. This circuit is for 8.4 volt to 2 series lithium ion batteries connection. That's where you can see this CS pin is getting connected with a V-Reg pin directly. And if it is connected like this, then it is for 8.4 volt. If you remove this, then it is for 4.2 volt. And there is a one resistor here, which is called RS, a series resistor or a sense resistor, you can call it as. And if you set this particular resistor value to a specific value, which is given in this data sheet, it will change the current at which this battery is getting charged. This is how this typical circuit looks like. And this is for 4.2 volt. And if you scroll a little bit down, this is how the IC looks like, a footprint or a pin diagram you can say. And this is how small this IC is. It's a QFN 16 pin IC, very small actually. And if I scroll a little bit down, this is how the internal block diagram of the IC looks like. And these are the parameters, electrical characteristic. If you want, you can read these all things to understand the IC much better way, and also the graphical representation of certain information which are absolutely necessary for the designer to understand this IC completely. And if I scroll a little bit down, you can see that pin configurations or pin functionalities are also discussed. This is again essential for you as a designer for the first time. I have studied the data sheet lot of time, and I have used this particular circuit more than 20 to 30 times in our project so far. Most of my projects are being delivered with the portable feature. If we want to go with a portable feature, then we need to add a battery, and whenever we add a battery, we always go with this particular IC only. So that's why I have read this entire datasheet, and it is absolutely necessary for you to design a hardware according to this IC. So make sure that you spend a little bit of time and read this entire information. And if I scroll a little bit down, you can get to know that how this particular IC can be interfaced with a microcontroller, so that we can get to know whether the IC is charging the battery right now, or charging is completed, or whatever happening in that particular IC. So it's a microcontroller interfaceable. And then if you go a little bit down, you can see here, this is how the set resistor or the R set resistor is helping us to get to know the battery charging current. It is determined by the resistance value of RS. If it is a 1 ohm resistor, then 100 milliampere of a current rating will be provided to the battery to charge. This is the slowest possible charging, 1 ohm resistor. If it is a 0.067 ohm, which is 67 milliohm, yes, it is in milliohm, then it is going to be a 1500 milliampere, which means a 1.5 ampere of a current rating. If it is a 0.05, which is a 50 ohms of resistance, then it is going to be a 2 ampere of charging. This charging is extremely fast and it may heat the entire module and inductor. So be careful while you are using this particular setting. I always prefer to go with this setting, which is a 1 ampere of a setting. That makes our job very smooth and very easy for most of our application. But again, choice is left to you. This is how the datasheet of this IC looks like. Now I'll jump into the schematic design, and I will refer one of the circuit which I designed in our previous project as a reference, so that I can speed up my schematic design activity. I'll go to the file, create a new project, and name this project under my name, and I'll name it as a charger circuit, or maybe a lithium ion charger circuit, right? So yeah, circuit, lithium ion battery charger circuit using TP5100 IC. Alright, so I'll just click on the save now, and a new file will be created here. I will rename the things as we always do. Alright, you can see that the circuit is ready, as I already copied it from my previous project. That is the beauty of easyEDA tool. And I have added a one connector here for the supply of a 12 volt. Again, this is not a 12 volt exactly. We can name it as a VCC. Why? Because we don't know. I mean, based on our requirement, we can short this resistor. That's why it is a 0 ohm. So that if we short it, then it becomes a 8.4 volt battery charging circuit. Or if it is not short, if it is open, then it is a 4.2 volt battery charging circuit. So single particular PCB or this particular design can be used for both the application, 8.4 volt as well as for 4.2 volt. Now let's jump into the design of PCB layout as we always do. Alright, now we are completed with this entire project. Here you can see that this is how the entire PCB looks like after complete routing. Again, the placement of these components are not so efficient as per the IPC standard or as per our company guidelines which we did in our previous project. However, it is absolutely passing the DRC error and also other fundamental errors. If you manufacture this PCB, it works phenomenally. There is no question about it. But still, there is a possibility to improve this PCB routing and placement of the component if a time is given. Since the video is going too far, more than 40 minutes, so I'm just cutting it down to whatever best possible in this video. Now you can see that this particular PCB is a combination of through-hole and SMD components. In previous designs, we usually went with only through-hole or maybe only SMD in recent 2 experiments. But right now, in this video, in this particular tutorial, we have explored the possibility of using a through-hole component as well as SMD components in combination. And also, this is the 2-layer PCB designing. So, beautiful project for your learning and understanding the concepts of real-time project development or real-time product design engineering. Upon that, I have given this R1 LED at the board edge only. Why? Because whenever a user wants to shift this entire module for a 8.4 volt, they must be able to access it very easily from the corner side. That's why it is given on the corner side only. If you can even push it to the board side, that is also still good one. But right now, I kept it there only. Nothing much complicated. And there are a couple of LEDs here to indicate whether it is charging or completed with the charging. All these things are given in the data sheet, and based on that only I have added it. So this is all about the entire project. This is how it looks in a 2D diagram, a top side view and a bottom side view. And in this tutorial, I have mentioned about the BAT plus and a ground and in plus for the indication for the user. And also I have created a copper 4 for the input voltage and copper 4 for the battery output, because these two are the very maximum current flowing point. Other than that, everything is okay. I mean, this inductor is also very high current flowing point, where I have given a 1 mm of track width or a 0.8 mm of track width, which is sufficient enough. So this is how the entire circuit looks like in a 2D, and this is how it looks like in the 3D design. Absolutely small one and absolutely a product level design which you can manufacture and use for your any project here and after. I think the board could be a 0.8 mm sufficient, because 1.6 mm is too thick for such kind of a small boards. So that's why I believe 0.8 mm is good one. And I'll show you one more very cool feature about this easyEDA, that is all about layer distance. If I make it a 10 mm, you can see that how these layers are architectured in fabrication. 10 mm is too much. Let's make it 2 mm probably. I think that is good one. Yes, 2 mm. You can see here. This skin color part is prepeg layer, a top copper layer, a bottom copper layer, top green mask or a top solder mask and a bottom solder mask, top silk layer and the components. And bottom side, we do not have any component. That's why we don't have any silk layer as well. If you add any silk layer detail here, maybe a logo of your company or your name or anything that you want to add here, then the bottom silk layer also comes into the picture. This is the beautiful part of easyEDA. In fact, you can dissect the entire PCB and see it how exactly it looks like. So let's make it back to 0, and this is how the entire integrated PCB looks like. This is all about the project, that is lithium-ion battery charging circuit using a TP5100 IC. I hope you enjoyed and understood the entire project, and I believe you are trying to design the same project by yourself. And if you get any questions while developing this one, feel free to ask me in the comment section. I'll answer as early as possible from my side. Thank you so much for watching this video, guys. I believe you understood the concept and designed a PCB by yourself. See you again in the next video. Until then, consider subscribing to our channel Linked Frequency and share this video with someone who may need it. See you again in the next video. Until then, tune yourself to make a difference.